Hey my dear friends of the underwater world, and welcome to my already announced tutorial. This time with the topic of gases under pressure, and with it the questions: why should you never hold your breath underwater, especially when scuba diving? And why a bottle feels like it contains less air as soon as I get into the lake with it. Before I start now, there are a few notes at the beginning, because in this tutorial I do things a bit differently than before. The first, there will be two small experiments here, and I ask everyone not to do them without sufficient diving experience, because these bodies that are used here create a strong buoyancy, even if it does not look like it. Um, you should definitively be able to tear there, and depending on where you want to do it, please get permission locally if necessary. Thanks again to the Dive for Life dive center in Siegburg, who made this possible for me here for this video. Then, at the evaluation, you will see that later I have done this with very simple means. Accordingly, measurement errors have been unavoidable, but the results are, for the framework in which we operate here, definitively satisfactory. Third, there is no live sound at the English version. I'm sorry. You will also notice a slight red tint on the surface and at shallow depth during the experiments on the video. This comes from the red filter used in front of the camera. I had to make a decision. Do I have a slight red tint at the surface or a better tint underwater? Since we were underwater a lot, I decided to go for it. If you want to know more about this, you can have a look at my tutorial about colors and why everything appears so blue underwater, which you can find in the highlights. And now to the last point. You are asked, do you like it, how I do it with the experiments? The video is longer, yes. Or is it too long? Is there a topic that interests you? Always here with it. Put it in the comments, write me a DM, or contact me in any other way. I'm always happy about suggestions, and if it's possible for me, I'll make a video about it. Now, enough chatter, the video will probably be long enough. We start directly with the first experiment. Hey guys, and welcome to the first experiment. I have this balloon with me, and I will take it with me on the dive down to about 20-meter depth. To compare the whole thing a little better, I have sketched the outline here on the board. Unfortunately, it's hard to see on the video, but you'll see it better later. And we'll meet again right below. Like this, we now have the balloon down at about 20-meter depth. As you can see, I can now get my fingers around the whole balloon quite well. We'll take a closer look when we go up again. We now record the size on the board and see each other again on the way up. There we are again, back at about 7-meter depth, and you can see very clearly I can't get around so well with my fingers. And here we are again at the surface. You have just seen it briefly. I can't get my fingers around the balloon anymore. So you definitively saw a change in volume. I will go into the physics of this again in a moment, but for now we will look at the second experiment. The second experiment is all about this plastic bottle. I'm going to deflate it as well as I can at the surface and take it back down to about 20 meter again. Fill it with air and seal it, and then we'll see what happens to the trapped air when we ascend. Welcome back, now down to 20 meter. If you looked very closely just now, you could see that the bottle was mostly empty of air. There was virtually nothing air coming out. Unfortunately, the filling with the octopus did not go as well as we had hoped, so we did the whole thing with the mouth. Always remember to keep breathing while scuba diving. Never hold your breath and always leave at least a little bit of bubbles, just to avoid a lung overexpansion injury. And unfortunately hard to see on the video, I tried to indicate it with my finger, the area of the bottle that is still filled with water at the end. Though this little bit here at the end of the bottle. So, at the neck of the bottle and everything else here is completely filled with air now. There we go again on the way up. I'm going to try to cut this all together as best as I can to responsibly fit. But pay attention to the parts of the bottle that I'm trying to highlight here with my fingers. They are still a little dented, and that's where you can really see the air working and expanding in the bottle, because these two dents are gradually being pushed out again. This is very easy to see, and you can really see how the air increases its volume due to the decreasing pressure. Currently we are in the area between 10 meters and 7 meters depth. What you can see very well in this video is that you can still squeeze the bottle very well with your hand, compress the air. We'll now take another look at how that it is at a shallower depth, and then we are back to the surface. There we are again, back after the safety stop, now at less than 5 meters depth. You could see it very briefly. You can still squeeze the bottle, but not as strong as before. We look at the whole thing now again on the surface, and then, although the second experiment is finished. Finally, we are back at the surface. If you look closely, you can see that you definitively can't compress the bottle as easily as before. Also good to see is how small is the water we have left in the bottle, and I'm going to open the whole thing now, and then you'll see how much air escapes here right away, and then you'll also see how much air you can still squeeze out of the bottle underwater. So there has definitively been some air in there. Thanks at this point to Fabio, which you can see in the picture behind me, for assisting us, and also for Martina for the filming. And we'll see you right back in the tutorial. So, and as already indicated in the first part, let's have another look at the physical basics. To a large extent, I refer again to the normal knowledge of physics that you could take in the course of your school time. Where I don't do that, there are two places on this slide where I go very briefly into the field of thermodynamics. I have indicated the corresponding source here, so if you want to know more, you can just read it. But otherwise, I'm in the opinion that everything that I put here on the slides and tell in addition on the soundtrack should be sufficient for the understanding. So, the basis for everything is the ideal gas equation, which is P times V is M times R times T. I'll come to that in a moment. Let's first look at the quantities in this equation. We have the pressure P in Newton per square meter. We have the volume V, which is best given in cubic meters, the mass or weight M in kilograms. R is the general gas constant, which has somewhat unusual unit, joule per kilogram Kelvin, and the temperature in a not so common unit, namely the Kelvin. We will come back to this in a moment. Now, first the question why we speak of ideal gas equation. For this equation, a few simplifications are made. I have put this on the slide. One assumes here that the molecules of the air are sufficiently far away from one another and a mutual influence can be assumed as non-existent. And this is also completely sufficient for our count of consideration here. So we don't have to complicate things unnecessarily. Let's have a quick look at what the equation says. So the product of pressure and volume is equal to the product of mass, temperature and this gas constant. We will see in a moment what this is useful for. I will now briefly go into the units and quantities of the equation, which may not be so familiar to everyone. For volume and mass or weight, I assume that everyone knows this. A little more unknown is perhaps the pressure given in Newton per square meter. The divers among you know this rather in the unit bar or psi if you use the imperial system. Here I would refer again to my other tutorial on pressure and what it actually is. Look at the highlights if you want to know more. The quintessence is 1 bar is simply 100,000 Newton per square meter. Though we just continue to calculate, and as I said, if you want to know more, just have a look at the other tutorial. The next thing is the gas constant. It depends on the considered substance. Since we have air here, it is 287 joules per kilogram Kelvin. If you want to know more, just have a look at the source on the previous slide. We keep this value here because we are only interested in normal air. So, now again to the temperature. Temperature itself is a topic I assume that everyone knows it, but probably not everyone knows the unit Kelvin. A bit more common, at least here in the German-speaking area, is the unit degree Celsius. Because there it is simply defined, we have 0 degrees Celsius, that's the point where water freezes to ice, and then it was said we still take the boiling point where water becomes steam, denote that with 100 degrees Celsius and divide the whole in between into 100 equal parts. And though this Celsius temperature scale was created, the Kelvin did it a bit different. He has taken the absolute 0 point with 0 Kelvin, approximately at minus 273.15 degrees Celsius. Colder it does not go in our universe anymore, and on this base the point is where water solidifies to ice that now no longer is 0 Kelvin, we had that already, but these are now just the 273.15 Kelvin. The simple thing about the Kelvin scale is that the change of degrees Celsius and Kelvin is identically. This means that we simply shift the 0 point downwards and then have another unit at the back. We will need this later for the formula, but you will see that in a moment. We don't need to go into it here. So, now we go back to the ideal gas equation. P times V is mRT. For the balloon, the whole thing is quite simply. Namely, the right side is constant. That means it stays the same. The mass we have in the balloon does not change anymore. If we would take the balloon and try to get his weight, it would always remain the same. Also, the gas constant does not change anymore because we have air in the balloon all the time and do not change anything in the content. And we also say within a certain range the temperature doesn't change anymore. So we still have in the environment the 26 degrees Celsius that we have here in the indoor diving center. That means the right side will not change anymore, and we abbreviate the whole thing with m times r times t is constant. That means only the left side will change now. And we'll take advantage of that now by taking a closer look at the whole thing with the balloon. It was mentioned before that I tried to record everything on the underwater panel. In the video it was a bit difficult to recognize. I have photographed the whole thing again and measured it. The larger circle was the balloon at the top of the surface, the smaller one at the bottom at around about 20 meter depth. As I said, it was all done with very simple means because the tracing was not really easy, but I used this now as a basis and took the diameter at 2 points to get the average value, though the mean value, to get at least a meaningful value for the volume. I calculate the balloon volume at the surface from the diameters 20 centimeters and 14 centimeters would be the average value 17 centimeters, and the volume at the surface calculated, and then proceeded with the values from the bottom again in the same way. There it was a little bit easier to draw. The diameters were 10.9 centimeters and 11.5 centimeters, so the average was 11.2 centimeters. And there we got the volume from the bottom, and as expected, it was much smaller. And with all this knowledge, we now go into the ideal gas equation. And it is still true that P times V is MRT, and we have at the surface, everyone knows this, an air pressure of round about 1 bar, so that's the 100,000 Newton per square meters, and there a balloon volume of 0.0206 cubic meters, and we can put the whole thing into the left side of our equation, P times V. In each case, at the surface, we got 2060 Newton meters. This way we say now is a constant value, and now we go down to the bottom, and I say we don't know the pressure here. So we know, of course, at 20 meter depth we have a pressure of around about the 3 bar, and now in freshwater it is a little bit different, but the difference is also very small. We have determined the volume before and calculate here again P times V, and say these are the 2060 Newton meters determined before, and can convert this after the P for the pressure on the ground, calculate and get, so for P at the ground, scarcely 350,000 Newton meters. This converted about 3.5 bar. We have previously that there is about 3 bar pressure there, and considering that the drawing was anything else but accurate, and we naturally has also a slight overpressure in the balloon at the surface, we arrive at a result that is still acceptable accurate. To get a feel for the numbers and how it all measures together, this is definitively fine. Of course, you can display and evaluate everything in much higher quality, but I simply this is good enough for us in this tutorial. So now we'll look at the whole thing again with the bottle, because here it's not longer simple. Why? Well, we could say again we don't know the P at the bottom, and to stay with the example from just now, we have a bottle with 1 liter volume, so converted the volume is 0.001 cubic meters, and if we take that now with the surface, then we would have again 1 bar air pressure. But of course this is not true. The air expands in the bottle, and this creates pressure on the bottle, because in the bottle, and this must then be of course greater than at the ground. The volume remains the same, but if we now simply insert these numbers, we would turn in circles and come not to any result. Why the whole thing is so? We have to include another variable that can change, and that is the temperature. I've summarized the whole thing on this slide. You have to imagine air as a collection of particles, so-called molecules. And if we now build up pressure, the particles in this space, for example the bottle, which can only expand to a limited extent, are squeezed together. But the particles are also moving all the time, and thus collide with each other, more of them. What happens when things collide? Friction is created, and this leads to a higher temperature. You can also test this. If you pump up your bike a bit more violently and then touch the valve of your pump, it can get really hot. And that also happens here. And we didn't take that into account. Also, I have no thermometer to measure the temperature curve in the bottle. And for this reason, we cannot continue with the calculation here. At least not in a practical way. I could, of course, create some numbers in my mind and we could calculate them, but that would not be practical and not interested for us in this tutorial. But the whole thing can also be done the other way around, namely when the air cools down. For example, when you take your tank from a room to a cold lake, and the pressure would decrease here. Why? The system, for example the tank, would now cool down. At the lake it may be colder in winter than in the house, and because of this the temperature would drop there, and there is less movement of the molecules. They don't bump into each other as often, and therefore they have less space to occupy, and based on that the pressure is decreasing again. You may all have noticed this before. You take a bottle with you, have it freshly filled, it is still around about 200 bar at the filling station, take it home, cools down a bit, and then there are still only 190 bar left. At least that's how it's always in my case. If I then go with the tank in the lake, have not really breathed out of it, and already there are again 10 bar less on the Finimeter. We can now briefly look at this as a numerical example where we have to rearrange the ideal gas equation a bit. We put the T on the left side, then only m times r remains on the right. For example, mass times gas constants, which remains constant again, and take the examples I have just given. So my tank still has, if I let stand it a few hours in my diving cellar, still 190 bar, because it has cooled down compared to the filling process where all the air was pressed in, and of course some friction has arisen. My bottle has 12 liters, so 0.012 cubic meters, and now let's just say that it is 20 degrees Celsius at home. Now we have to convert that into Kelvin. I mentioned earlier it's pretty easy. We just put 273.15 Kelvin on it, then we have 293.15 Kelvin, and with that we go into the lake. Now the question is how much pressure I still have in my bottle when I go into the lake with it, and then wait for my body at the surface. And the temperature in the bottle has also completely adjusted to the outside temperature. In practice, of course, this takes a little time, but it should serve as a small experiment. The volume remains the same, my bottle neither gets bigger or smaller, and the temperature in the lake is 4 degrees Celsius. That means 277.15 Kelvin. Now we put the whole again into the ideal gas equation. So first the whole values for home, calculate everything, the numerical values are here, and come to 777.76 Newton meter per Kelvin. Since we divided before by the temperature, we have here of course also another unit. And look at the whole now at the lake. The equation is here, so again only the left side, P times V divided by T. The whole thing we convert now to P and get out here a value of approximately 180 bar. This is exactly what happens to me when I dive in winter at the lake. As soon as I'm in the water, my bottle loses about 10 bar. There are people who therefore fill the bottle a little more to start with 200 bar. You can do that. The bottles are designed up to 230 bar, but that also depends on the filling station, if they do that and if you still safe with it. Okay. So we have in any case answered the second question of the tutorial, namely why my bottle suddenly appears emptier when I go into the lake with it. I still owe you one answer, which I have now somewhat suppressed, namely why we should never hold our breath when scuba diving. And that is actually quite simple. Let's look again at the example with the bottle. We have filled the bottles at the bottom and screwed them shut. And now imagine that this bottle would have been your lungs. That means you breathe in underwater, keep your mouth closed and go to surface with it. You could see how the bottles was curved outward and how much air escaped at the end, almost explosively at the first moment. Your lungs are not quite as sturdy as the bottle. They would definitively start to rupture sooner and you would suffer a bad injury. So think about it for yourself. If you want to try this yourself, I would definitively advise against it, especially at shallow depths. These pressure gradients are pretty violent, so never stop breathing underwater. I'll end the tutorial at this point. It's become quite long, so I hope you stayed with me until the end. Stay healthy and I'll see you at the next time. Ciao!